Hello and welcome everyone to my today's session, which is on solving equations in Wolfram language. And I'll be using Mathematica desktop today to conduct this session. This is going to be a very interesting session as well because, as you know, in Mathematica, it has the combination of both the symbolic as well as the numeric uh, capability to solve equations. And today, the major of my focus in this session will be on the symbolic side of the capability that Wolfram language has to offer. And you will notice that how automatically most of these things can be assessed through a small number of exceptionally power functions. And we'll be taking a deep look on all of these functions today in my session. And I'll be giving step-by-step way of utilizing these functions for each and every instances. As you know, because Mathematica has a very vast breadth to cover, I may not be able to compact all of those things within today's lecture. But today will be a first step into that direction. So without wasting any time, let's move forward and see equation solving in Wolfram language in action. So first of all, couple of things I want you to understand. That in Wolfram language, in Mathematica, x is equal to 4. This is basically a direct assignment. So what it does, it set the value of x is equal to 4. So whenever I call this variable x, somewhere x like 2x, it will give 2 multiplied by 4 because it is a assignment. Whereas when I write x double equal 4, what it is going to do over here, it is going to check. This will be like a test equation now. Is the value of s is equal to 4? And this will give me true. If I have given us some other value like 6, it would have said that this is the false value. So basically, whenever you enter double equal sign, it is basically testing that if the right hand side is equal to the left hand side, and the result will be either a true or a false. Similarly, so like if I say 3 plus 3, and if I say double equals 6, it will give me true. So it is very important that you do not confuse with x is equal to y with x double equal to y. And if you want to clear any variable, you can just type here x, and now x is clear. So now when I call x, there is nothing stored in this variable. So Wolfram language treats equation as logical statements. So if you type the equation like in this format, like x squared plus 2 times x minus 7 double equal to 0. So this Wolfram language system interprets this as a logical statement, which shows that minus 7 plus 2x plus x squared is equal to 0 over here in this scenario. And you can assign a name to this equation as well. So I can say, okay, this is the equation. And now this whole equation is saved in a variable. Another way to clear this variable is a shortcut way is I can also write a equation and I can give it like a dot value. So this is also clears the values stored into this variable. So this is a very basic step to understand how you define or write an equation in Mathematica. Now, Wolfram language can find exact solutions to equation. And for that, we have a function called solve. So solve, you give it an argument and it will solve the equation giving the list of rules for x. So this is basically the syntax where you have like solve left hand side is double equal to right hand side, and you are telling that solve it with respect to x. So for example, you have an equation like a times x plus b double is equal to c, and you want to solve it for x. So you will use a function called solve, double brackets given the argument, and you have to tell Wolfram language you have to solve it with respect to x. So c is something values here, so I need to clear c first. So once value in the clear is done, it solves me for the value of that. Now let's solve a quadratic equation. So if I have to solve a quadratic equation, I have, let's say, like x squared plus 2 times x minus 7 double is equal to 0 with respect to x, and it will give me the result for that. Please note that there is a space between 2 and x in this scenario, which is understandable. But if you are writing two variables like together, ax or bx, or like a couple of digits together, it might take it as it will take it as a single variable. So it's always a good practice. So if you have a different variables, you keep a small gap into that, and Wolfram language and Mathematica automatically understand that this is a multiplication between them. So you see from here that this gives the two solutions to the quadratic equation, and the solutions are given as a replacements of x. So the advantage of having the replacements for x is that you can now get a list of actual solutions for x by applying the rules generated by solve. So like, for example, if I say x and I say replace by the last result, and you say now I only get the values, and now I can use it further into my calculations if I need to be. So you can use the replace all function also, and you will see the advantage of this replace all when we'll be verifying the differential equations later today. In the meantime, if you have any questions, feel free to write that in the chats in the comment section, and I will take a look in the meantime, or after the session I will take a look and I'll answer those. But it's a good way you can just register your question there also. So let's move forward and see how you can solve equations which have more than one variable. So for example, you have an equation like x plus y 0, and then you have an equation like x minus y is equal to 10. So these are two equations you want to solve for. So you know, in Mathematica, when you have to give a list, you surround that list under curly braces, and the function still we are using is solve. So we give the list of the equations, and then we need to tell it what are the variables we need to solve for. So we know that these are two variables x and y we need to solve for, and then we can solve it. Solve x plus y is equal to 0, x minus y is equal to 10. Strange. Let's rewrite it. Maybe I have some values stored somewhere. Okay, so this is how it is, and you can see I can now solve it for more than two variables also by giving double equal to sign, giving the list of them, telling Mathematica the list of variables to solve for, and it gives me the result for that. Just having all the equations in the curly braces over here. Let's see, solve equation always tries to give you explicit formulas for the solutions to equations. It is a fundamental mathematical fact that for equations of degree 5 or higher, it is no longer possible in general to give explicit formulas for solutions in terms of radicals. So if you have an algebraic equation in one variable and the highest power of variable is at most 4, then Wolfram language can always give you the formulas for solutions. It can also solve some equations that involve higher powers, like x raised to power 6. Now, you must be wondering how to solve equations for those where it is impossible to explicitly get algebraic formulas. And for that, in Wolfram language, we use a function which gives the results in root objects. So let's take a look at that. So there are some equations for which it is mathematically impossible to find explicit formulas for the solutions. So in Wolfram language, uses root objects to represent the solution in this case. So in this case, example, x raised to power 5, when we solve it in Wolfram language uses root objects to represent the solutions. Even though you cannot get explicit formulas, but you can still evaluate the solution numerically. So we can use a much faster way is to use nsolve function, and it will give us the numerical result of this. Now let's take a quick look on solving equations that are not explicitly in the form of polynomials. So here is an equation involving square roots. So we are solving square root of x plus square root of 1 plus x is equal to a with respect to x. Here is another example having log of x plus log of 1 minus x is equal to a, and solving it for variable x. So in addition to being able to solve purely algebraic equations, the Wolfram language can also solve equations involving other functions. So for example, solve sine of x is equal to 1 by 2 half with respect to x. And you see Wolfram gives an expressional condition. Their value is y by 6, pi by 6 and 5 pi by 6. It is important to realize that an equation such as sine of x is equal to a actually has an infinite number of possible solutions. In this case, differing by multiples of 2 pi. And maybe we can see that quickly by if we do a plot of this. We can see this in visual form also. So if we do a plot of sine of x with 0.5, the other is equal to, and we say, let's see if we from 0 to 10 pi. And you can see there are multiple solutions which are varying with the different multiples of 2 pi. Similarly, in certain types, there are no explicit closed form solution for these transcendental equations like this, like cos of x is equal to x. So there is no explicit solution for that. So Wolfram language will give you a warning in this case, and it will tell you that these types of systems cannot be solved with the methods available to solve. So what to do in certain cases? In these situations, we'll be using a function called find root. So what does find root does? It will give you an approximate numerical solution by giving a start value of x. So the closest value of the intersection starting from x is equal to 0, it will give you the find root for that. We are going to take a look at the find root in another slide also. But at this moment, I just wanted to make you know that certain scenarios which cannot be solved because of the explicit closed form, you can use find root function in those scenarios. Let's now move forward and take a look on those equations which involve symbolic functions or inverse functions. So solve function can also handle equations involving symbolic functions. In such cases, it again prints a warning, as you see over here, but then gives a result in terms of a formal inverse function. So when I do solve function of x is equal to a with x, it says that inverse function has to be used, but it gives the Wolfram language gives the results for that. And you can also see the structure of this. So if I say input form and I take the last output, I can see the input form for that also. Or I can have this like inverse function of maybe 10, and I can quickly take an example of inverse function to get an explicit solution over here. So how to solve simultaneous equations now? So you can use Wolfram language to solve sets of simultaneous equations. You simply give the list of equations in curly braces and specify the list of variables to solve for. So for example, solve ax plus y is equal to 0, 2x plus 1 minus 1 y is equal to 0, and this you can solve this for using the solve function. A more complicated example can be this one. So all you have to do is just give the equations in a list and let Mathematica know the variables you need to solve for. So Wolfram language can solve any set of simultaneous linear or polynomial equations. But what happens if there is no consistent solution? So there are certain scenarios where, or certain equations, there is no guarantee that there exists any consistent solution for a particular variable. So for example, in this example, you see there is no solution. So Wolfram language returns empty brackets, indicating that the set of solution is empty. So there is no consistent solution to this equation also. But what to do in these scenarios? So the general question of whether a set of equations has any consistent solution is quite subtle one. For example, for most variables of a, the equation x is equal to 1 and x is equal to a will be inconsistent. But there is a possible solution here. So if a is equal to 1 here, then the equations do have a solution. So solve is set to give you a generic solution. It discards any solution that exists only when special constraints between parameters are satisfied. So in those scenarios, if you use reduce instead of solve, the Wolfram language will keep all the possible solutions to the set of equations, including those that require special conditions on parameters. So this shows that the equations have a solution only when a is equal to 1. The notion a is equal to 1 and x is equal to 1 represents the requirement that both a is equal to 1 and x is equal to 1 should be true in this case to get an answer. So solve is set up to give you only generic solutions. But if you want to have solutions with all the special constraints between the parameters, you will use a reduce function. So similarly, now instead of solve, if we use a reduce function, it will tell us all the possible complete set of possible solutions. The answer is stated in terms of a combination of simpler equations. So double and indicates equations that must simultaneously be true. So these both have to be true to get a solution for that. Whereas when you have this like Pell it indicates alternatives. So when I use another equation of reduce, it says that b is equal to 0 and a is equal to 0, then you can get a result for solution for that. Alternatively, if a is not equal to 0, then x has to be b over a. So in this way, you can get all the results using reduce function, but you use solve function to get all the generic solutions to the equations. Okay. Let's move forward and see how are you going to handle equations over real numbers or integers. So as you see, reduce also has powerful capabilities for handling equations over real numbers or integers. So this reduces the equation assuming x and y are complex. So you can also do it for reals. So if I press Command L does is takes the above input again, and then if I want to solve it only for reals, I can just say for reals. Or I can like Command L and I say, okay, I only want this for integers. And I get all the possible solutions for this. So this is an and this is an alternative. So this way you can get the equations over real numbers or integers also. Now let's move forward, and we'll now take a numerical solution to equations. So solve and find root are two major functions we can use. So you notice earlier we used solve, and then we gave it an equation like x squared plus 4x minus 7, 0, and with respect to x, and we solve that. So similarly, we can now use find root. So what find root function will be working? It's giving left hand side is equal to right hand side. We give the variable, and we have to give a starting point from to search from. So this is very important to understand. So let's understand this by having a visualization. So maybe if I do like plot of cos of x, I don't know why my computer is typing double x. And let's give this both, because this is the range, and the range of x will be maybe from -1 to 1. Yeah. So you can see from here the find root will get and try to approximate the intersection of this value for me. So this is what the find root is going to find out for me. So if I do like find root of cos of x is equal to x, and for x, and the starting value point from where I have to search is 0. So approximately at 0.739085, it will give me the point of the intersection, and that progressively tries to get closer and closer to a solution. So if your equation has several solutions, find root always return the first solution it first find. So if there is another point where it is intersection, it will be giving me the two results over there. So for example, let's see here. So if I have like find root, and I say log of x, and this is equal to of x, and -5 maybe, and then I have to give x, and I have to give the starting point of x as well. So in this scenario, if I give the starting point of 0.1, so what it will do, it will give me the value for this. at in the 0.016. But if I give this the value like instead of starting point I say 0.1, I say okay, give me 1.5. The find root is going to find the value at 1.7. So this is happening because it is intersecting at more than 1 point. And you may be wondering, why is that so? So you can also see that by visualizing this. So if I take a this equation goes back there. So I'll copy it from here. And I'll paste it here. And the value from 0